yesterday we didn't do much, right? We determined the automorphism group of the unit disk using Schwarz lemma and the maximum modulus theorem. So they are all some special kinds of Mobius transformations multiplied by rotations. And then we looked at isolated singularities. And isolated singularity means in a punctured neighborhood of Z0, the function is analytic. So at that point Z0 itself, it may or may not be analytic. So in that case, you say that it is an isolated singularity. An isolated singularity, isolated singularities are classified into three types: removable singularities, poles, and essential singularities. So removable singularities are those for which you can redefine the function at that point Z0 so that it becomes analytic in the whole neighborhood, including at Z0. Poles are those which become unbounded in the neighborhood of that point. The function goes to infinity in the neighborhood of that point. And essential singularities are those for which there is no definite limit as the function when the point approaches Z0, the function. So we classified this in terms of the Laurent series. Any annulus, we saw that a function which is analytic in an annulus can be expanded in a series of powers, both positive and negative powers of Z minus Z0. So sigma minus infinity to infinity for an Z minus Z0 power n. Okay. So essential singularity means the negative powers are infinite in number, right? An is non-zero for infinitely many negative n. In that case, you say that it's an essential singularity. If there are only finitely many non-zero negative coefficients, then it is a pole. And if all the negative coefficients are 0, then you have a removable singularity. In essence, a removable singularity is no singularity at all, right? So just you can remove the singularity, so it becomes regular at that point. And we saw, at least we mentioned, that in a punctured neighborhood of an essential singularity, the range of the function is dense in the complex plane. It comes arbitrarily close to any complex number. So we also made some observations, like a polynomial has a polynomial of degree n has a pole of order n at infinity. So the behavior at infinity is defined in terms of behavior at 0 for the function f of 1 over z. Right? So a polynomial has a pole at infinity. An entire function which is not a polynomial has an essential singularity at infinity. So for example, if you apply the Parthasarathy theorem to an entire function, what does that say? In a neighborhood of infinity, the function takes arbitrarily close values to any given complex. That is, the range is dense. So what is the neighborhood of infinity? Exteriors of disks, let's say, right? Outside any disk. For mod z greater than r, for any r, the range of the function in that domain is dense in C, right? Because infinity is an essential singularity for the function, entire function. So today, let's try to wrap up things at least at a reasonable point. So we'll briefly look at conformal mappings, which is the Riemannian viewpoint. Nobody else means neither Cauchy nor Weierstrass considered these geometric properties of analytic functions. So conformal mapping is about certain geometric properties of analytic functions, right? So we'll have a brief look at this. So it's essentially a point of view of Riemann. But before that, let me make a couple of observations of related to what we were doing earlier. So we had, of course, talked about zeros of an analytic function and the maximum modulus principle and so on. There is another important property of an analytic function, namely that a non-constant analytic function maps open sets to open sets. It is an open map. So what you can call as open mapping theorem. Because you have an open mapping theorem in functional analysis. That's it. So here it is non-constant analytic functions map open sets to open sets. This can be proved using the identity theorem, for example. Or you can also actually, first of all, prove a very interesting result about the local behavior of analytic functions. So let me state that result and then see that the open mapping theorem that I stated is going to be an immediate consequence of this result. So it's about counting zeros locally of an analytic function. So I'm not going to prove this theorem, just suppose f is analytic in, say, in a disk around Z0. If you look at fz minus z0, fz0, of course, this is 0 at, this is an analytic function, this is 0 at z0, right? So, non-constant, okay? So, this has a 0 at z0, suppose it's 0 of order k. Say, so the 0 is of order k, then positive numbers epsilon and delta such that so you're going to say something about a disk of radius epsilon around z naught and a disk of radius delta around fz naught, right? So you have such that what? For any point in this disk, there are exactly k points in this disk which takes that value. Right? If you take a point, say zeta here, for any zeta in this disk, there are n points, there are k points in this disk which are mapped to this zeta by f. Okay? So in other words, the equation f takes a value zeta means that this function, I mean this is 0 or this has k solutions in here. And moreover, we can arrange that these are all the zeros that you get are all simple zeros. Has exactly for mod zeta minus fz naught less than delta has exactly k solutions in so that means there are points, say z1, z2, zk in this disk such that f of zj is equal to zeta. Maybe I should have written the switch the epsilon and delta, right? That is usual. Of course, it doesn't matter, but usually continuity or anything, mod z minus z naught less than delta, mod f minus fz minus f delta is less than epsilon. So in particular, the image of this disk here is contained in this disk, right? So f of, if you call this as u, this as v, f of u is contained in v. So in particular, it says that if you take any point in the range of f and I take a neighborhood of that point, there is a neighborhood of that of z naught which is mapped into this, right? The delta neighborhood of z naught is mapped into an epsilon neighborhood of fz naught. Okay? So, in particular, f is an open map. If you take Z naught, and I take a neighborhood of Z naught, the image contains an open set around Z naught. Right? If you take any open neighborhood of Z naught, it's going to contain a disk. Right? Then the image of the neighborhood is going to contain the image of this this disk there, but this disk contains this other disk there around Fz naught. So in particular, F is an open map. Of course, if you start with an analytic function in a domain, it's going to be analytic in some disk there, right? Here we are starting with a disk, but you can apply this to any disk in the domain. So any open set in the domain is going to be mapped into an open set in the range. So in this case, actually, the neighborhood of any neighborhood of Fz naught contains the image of a neighborhood of Z naught. Okay, maybe that you can write that way. What is it I'm saying? It's mapped to a neighborhood of Fz naught. So as a corollary of this result, you have the open mapping theorem. A non-constant is the open mapping theorem. A non-constant analytic function maps open sets to open sets. So the image of a open connected set under an analytic function, again an open connected set. Connectedness, of course, is preserved by continuity itself. So openness is preserved by analyticity. The corollary of this is again the maximum modulus theorem. A non-constant analytic function doesn't have a local maximum. So geometrically, so if you take any point in the range, right, it's going to contain a neighborhood, the image of a neighborhood of a point here, right? So, local maximum means what? In a disk here, say Fz naught, if a function has a local maximum at Z naught, in a disk around Z naught, mod Fz naught is the maximum. Mod Fz is less than or equal to mod fz0 for every z in that disk. But if you take fz0 here, so look at the neighborhood here. Okay, so you have an open set, the image. So this image of this disk is mapped into this disk by the open mapping theorem. Okay, so fz0 is here, but you see, what is the modulus? Is the distance from the origin, right? So if the origin is somewhere here, so all these points are in the range. So take any point, there is, if this is fz0, so the distance is going to be, of this point, say, is going to be bigger than the distance to fz0 from the origin. If this is the origin, so modulus, if this is modulus fz0, so you have points all around it which are in the range. So at least, in fact, there will be many points in that disk which are at a distance greater than modulus of fz0. Right? So fz0 cannot be a maximum in a neighborhood. Or if you want to write, suppose fz is less than or equal to mod fz0 for in a neighborhood, say, let us say, less than r. That is, function has a local maximum at z0. Then the range of this disk, call this disk as D, is contained in all W, mod W is less than or equal to mod fz0. Right? That's what this means. For all points in the disk, you have this is less than or equal to that. So this range is contained in this disk. Right? So, but this is not a neighborhood of fz0. Right? fz0 is modulus fz0 is on the boundary of this disk. You are looking at all W with mod W less than or equal to fz0 is somewhere here. Okay? So this is certainly not a neighborhood of the fz0. So this cannot happen unless the function is a constant by the open mapping theorem. Right? The open mapping theorem says that a neighborhood of z0 is mapped to a neighborhood of fz0. But here, fz0 is going to be on the boundary of this neighborhood. Right? So this cannot be unless f is a constant. Right? So this is not a neighborhood. Therefore, f is a constant. That is, if the function has a local maximum, then it's a constant. That's the conclusion. So the maximum modulus principle is immediate from the open mapping theorem. Anyway, so let us say something about so this is about so if you have an analytic function, any curve in the domain is mapped to a curve in the range, right? How do you measure angle between two curves at a point of intersection. By definition, angle between two curves is the angle between the tangents at that point, right? So of course you assume that the curves are C1 as usual, so that the tangents make sense. So you have two curves C1 and C2 at Z0. So the angle between the curve is this angle. So you look at, you have a function f. So f composed with C1, f composed with C2, let us say. So measure the angles for these. So this is the angle. Let me call this. Oriented angle, right? Direction also. So the question is, when are the two angles the same? Right? Angle between two curves at a point Z0 and the angle between the image curves at FZ0. If these two intersect at Z0, the image curve will intersect at FZ0, right? Okay, so let us start by looking at some simple examples. Okay. What does the function z bar do? So if this is z, z bar is a reflection about the real axis. So what happens in this case? You take straight lines themselves, for example. If you the real axis and this line, for example, if you take, right? The image of the real axis is itself under z bar, and the image of this line is this. Now the angle is this. So the magnitude remains the same, but the orientation is the opposite in this case. Right? So magnitude preserved, orientation reversed. For this example. What about the function z square? So how do you measure the angle? In terms of the amplitude, right? Or the argument, as you say. Right? Theta, of course, determined up to a multiple of 2 pi. You take the principal values. So this is the angle made. So this is your angle, theta here. Okay? The real axis and this OZ. So if you take two lines like this, amplitude of this minus the amplitude of that, right? The argument amplitude, okay? So this is what is called the argument. This is mod z e power I theta. Theta is the argument of z. Of course, the argument of z1, z2 is what? R1 e to the I theta 1, R2 e to the I theta 2. Product is going to be R1, R2 e to the I theta 1 plus theta 2. So the sum argument of a product is the sum of the arguments. Of course, argument makes sense only for non-zero complex numbers. Okay, otherwise it's not defined. So what happens to the argument under the function z square? If the argument of z is theta, argument of z square is 2 theta. So whatever curve that you are going to consider at 0, the arguments are going to be doubled, right? So if you have theta 1 minus theta 2, the one is theta 1, the other is theta 2, so the difference is theta 1 minus theta 2, the angle between these two. If you look at the corresponding images, it will going to be twice theta 1 minus theta 2. So in this case, the angle between the image curves is going to be double the angle between the original curves. If you are starting with, you start with, say, for example, 2 lines through the origin. Look at whatever, I'm not going to draw the correct figure. What happens to the straight lines under z square? I'm not going to discuss that. But, so if this is theta, the image curves, this is going to be 2 theta. Suppose this are the images of these two. So this is again 0, okay? 0 goes to 0. So 2 curves intersecting at 0, if you take, the image curves also intersect at 0, but the angle there is doubled. So this does not even preserve the magnitude of the angle. In absolute value. Of course, it can be in the opposite orientation also. Anyway, the magnitude is double. So, under what conditions is the angle preserved in both magnitude and orientation? That's what we want to see. Right? What do you know about this function z bar? It's not analytic, of course. Right? So that could be the reason why the angle was, when I say angle preserving, both in magnitude and orientation. Okay. Otherwise, you will say magnitude it preserved magnitude, it preserves orientation. If it preserves both, I will just say angle is preserved. So is this the reason why this does not preserve angles? But what about the other example? Z square. That is analytic, but it still does not preserve angles. So there is something more than that, more than analyticity that you need. Right? Of course, it's very easy to see something. In this case, we are looking at 0. The curves at 0, the image curves at the image point. So this is analytic, all right. So what is the derivative? 2z. What is the value at 0? 0. So the derivative at the point is 0. The analytic, but the derivative is 0 at that point. Here it is not even analytic. So if you eliminate both these possibilities, that means if you have a function which is analytic with non-zero derivative at a point z0, then it preserves angles. Okay, that's almost obvious, as we'll see. So of course, yeah, so the terminology is that such a map is said to be conformal. So maybe we'll write that and then write down the result. A map of course, we want to talk about derivatives of curves and so on, tangents to curves and so on. So you need some regularity condition here. So assume that it's C1, real differentiable. That's all. Okay? That means which has C1, let us say. A C1 map you can write. When do you say F is C1? F is U plus IB. So U and V both are C1. That means it have continuous first partial derivatives. Is said to be conformal at Z0 in omega if it preserves angles at Z0. That means if it preserves angles of curves at Z0. That means if C1 on, shall we write, change notation, instead of writing C1 and C2, let's write gamma 1, gamma 2 or something, alpha 1, alpha 2. So F composed with alpha 1 and F composed with alpha 2 will be the image curves. So the angle between then the angle between alpha 1 and alpha 2 Z naught is the same as angle between f composed with alpha 1 and f composed with alpha 2 at f of z naught, both in magnitude and orientation. Or sign of the angle, sense. And of course, you say that f is conformal in omega if it is conformal at every point of omega. So by definition, angle between two curves is the angle between the tangents. So what are the tangents? Suppose so you're starting with z naught. So both alpha 1 and alpha 2 pass through z naught. So let's say alpha 1 t naught is z naught, right? Alpha 1 is a curve through z naught means what? Alpha 1 t equal to z naught for some t, call that as t naught. So what is the, you have to look at alpha 1 prime or alpha 1 dot if you want, derivative with respect to t. Okay, so these are the tangents. So the angle between them is the difference in the arguments, right? The image curves, if you take a function f, you have to look at the angle between this and we want to see when this is same as the angle between this. So suppose, for example, that f is analytic and with a non-zero derivative. On omega, whatever. Derivative at the point concerned is non-zero. So, but what is this in this case? If you assume that f is analytic, right, the chain rule. So what is the argument of this? So when you take the difference, this is z naught, right? Alpha t naught equals z naught, let's say. So what is the difference, therefore? Argument You have j equal to 1, 2, right? So subtract. This is common, f prime z naught. So that will go off and give you so that means the angle between the image curves is the same as the angle between the original curves. Where do you need this? Now, if it was 0, you can't take arguments, right? It's not defined. Both in magnitude and orientation. What is the meaning of saying that orientation is reversed? In this, if you take 2 minus 1 here, if you get 1 minus 2, right? If you take alpha 2, alpha 1, if you get that it is alpha 1 minus alpha 2, then the orientation is reversed. One you go like this, the other come the other. But now everything is fine. So if the function is analytic with a non-zero derivative, then it is conformal. Right? Any analytic function with non-zero derivative is conformal. So this is a proposition. The converse is also true. If a map is conformal, then it's analytic and the derivative is non-zero. So that's what we want to show next. But first, let's look at a simple example. Suppose fz at fz naught, of course. So it's a combination of z and z bar. Okay. So when does this preserve angles? You can make a guess, of course. Right? As long as z bar is present, you're going to have trouble. So this is going to preserve angles only when b is 0. Suppose this preserves angles. Okay. So let us take two lines and look at the images and see what we get. One of the lines let's take as real axis to make things simple. Okay, so what is the image of the real axis under this? The line through the origin and a plus b. And z is real, so z is x. Okay, so you just get ax plus bx. So the image of the real axis under f the line through a plus b and the origin. On the other hand, take any direction, that means any, how do you fix a direction in the plane? By fixing a point on the unit circle, right? Take any lambda on the unit circle, mod z equal to 1, take any point lambda on the unit circle, look at the line joining 0 and lambda. Or the whole line if you want, doesn't matter. So what is the image? So for lambda, mod lambda equal to 1, the image of the line through 0 and lambda is a lambda plus b lambda bar. So the angle between them angle between this and angle between that the two lines between, let's say, 1 and 2 is argument of this minus argument of that what is the angle between the pre-images? So the real axis here and this line here. So the argument in that case is the argument of lambda. So this is the real axis, this is lambda. So this line is mapped to that. This line is mapped to this. So if f preserves angles, if f is conformal, at 0, then this is equal to argument of lambda, right? This angle is the argument of lambda. So what do you get? Argument of lambda is equal to correct? Now you pull out a lambda from here, So this I can write as take out a lambda. So again, the argument of a product here. So argument of lambda plus argument of a plus b lambda bar lambda minus argument of a plus b. So argument lambda cancels off and gives you so this is for what lambda? This is for any lambda with modulus lambda is 1. Right? So if lambda keeps changing on the unit circle, okay, so this is going to keep changing. Whereas the right hand side is independent of lambda. So when is this possible? Only when this term here is absent, right? That means B is 0. Because lambda bar by lambda is non-zero, modulus 1. So the only way where this term can go off is when B is 0. Okay, so this is true for every lambda of modulus 1. So this implies okay, is this okay? As lambda keeps changing, if B is not 0, as lambda keeps changing over the entire circle, this argument is going to keep changing, right? So the only way that this can happen is when B is 0. So that's what we thought in the beginning, and so that's what we proved. So if AZ plus BZ bar preserves straight lines through the origin, then B must be, not preserves angles between straight lines, not preserves straight lines, preserves angles between straight lines if and only if B is 0. Okay, so now we can prove the converse of what we had. If you have a conformal map, then it must be analytic with a non-zero derivative. So if F is conformal, then F is analytic and has non-zero derivative. I am being a little sloppy today. I'm not writing everything, omega domain, this, that, and all that, okay? At the point Z0, etc. So suppose, so you want to look at a curve alpha and the image of that curve under this function f, with this assumption on f. So suppose your curve alpha is given by t going to zt, which you can write as xt plus it, iyt. So f, take whatever beta to be f of alpha t, beta t. This is the image curve. Say okay, you can call it Wt if you want. Okay. T going to Wt. So of course now you are not assuming that f is analytic, so you can't write this f prime alpha t alpha prime t. Okay, but you can still use the chain rule. You write f as u plus iv, right? Use the chain rule. You will get. Just think of f as a function of x and y now, right? So fx dx by dt plus I times whatever, right? I mean, so w prime t will be we'll get an I suppose. What is fx now? Fx is 2x plus ivx, and similarly fy. I'm going to write down which you must check. I mean, just multiply out and check. So this is A is remember fx is ux plus ivx and so on and so forth. So just write it down and check that. So this will give you what? So if f is conformal, so it preserves angles. So now this will have to preserve angles. So this is the derivative of what? This az plus t, I mean az of t plus bz bar of t, derivative of that. So that's going to preserve angles only when b is 0, that we have observed. Okay. So if f preserves angles, then A is at t where A and B are like this. Okay. So from what we have seen earlier, therefore B is 0 from our earlier observation. But what does B equal to 0 give you? Fx so this is ux plus ivx plus I times uy so ux minus vy plus I times uy plus vx. So this is 0 mean, of course, all evaluated at a suitable point, right? At t naught or whatever, z naught, etc. So this means lo and behold, so these are the Cauchy-Riemann equations. So in other words, if f is conformal, u and v must satisfy the Cauchy-Riemann equations. Of course, already by assumption f is a C1 function. So u and v have continuous first partial derivative. And we know u and v have continuous first partial derivatives and satisfy Cauchy-Riemann equation, then f is analytic. Right? Since u, v are C1, this implies f is analytic. And what is the derivative? What is f prime? What is a prime in terms of u and v? F prime is ux plus ivx. Right? Is also ui. Tell me, when you know that the limit exists, the definition of derivative, so you vary only the x coordinate, keeping y fixed, so you get the partial with respect to x. Similarly, keep x fixed, vary y, you will get the other one. So what will you get here? Huh? Vy. That's how we got the Cauchy-Riemann equations to start with. Okay. So you can write f prime as half of this plus this. This is f. I mean, this is f prime. This is also f prime. So if you add, you'll get twice f prime. So f prime is half of this. That will be just here. Non-zero. Why is A non-zero? So once we say this non-zero, we are done. Okay? Non-zero derivative. Non-zero except in trivial cases. So if you omit the trivial case. So if you combine the two, therefore, you get that f is conformal if and only if it is analytic with a non-zero derivative. Right? Because now you know why z square was not conformal. The derivative was 0 there. Okay. So a quick example, look at Mobius transformations. What is the derivative? Just calculate quickly and tell me. that correct? Into something. What is the derivative? Tell me. Correct? Of course, this is analytic, except where the denominator is 0, is 1 point where the denominator is 0. But so when it is conformal, and the derivative is not 0, it means AD minus BC is not 0, right? Conformal for only if that is the matrix ABCD is a non-singular matrix. So that means, in other words, GL2C is acting. What is GL2C? Non-singular, right? General linear group, GLNC in general, and by N non-singular matrices. So all non-singular matrices act conformally via the Mobius transformations.